is the 17th lecture on DSP, and our topic today is continuation of linear phase filters, and we shall also talk about a very interesting class of filters which comprises a set, and they are known as complementary filters, and this is where the importance of all pass filters shall be demonstrated. In the last lecture, we talked about all pass filters. There are zero locations. Zero locations have mirror image, I beg your pardon. The poles and zeros have mirror image symmetry. That is, poles and zeros occur in reciprocal pairs. As a result, all pass filters are necessarily maximum phase filters. None of their zeros can be inside the unit circle. And we also said that they are lossless bounded real function, provided we take the form, the form that we shall talk about is d and z, and the numerator shall be z to the minus n dn of z inverse. That is, the magnitude is normalized to unity, then they are lossless bounded real functions. We also stated a theorem that the magnitude of an all pass filter is bounded by this inequality, 1 for mod z equal to greater than less than 1, and I asked you to prove it. The proof is not very simple. Try it out, and if you cannot do it, let me know. We also introduced the comb filters. Because of the shape of the frequency response, they are called comb, and comb filters can be obtained from any filter which has one pass band or one stop band, or both one pass band and one stop band, by changing z to z to the power l, and then we get g of z as equal to h of z to the power l, which has multiple pass bands and multiple stop bands. And one of the most important uses of such filters are in the elimination of periodic interference, like the 50 Hertz signal in a biomedical signal processing situation. We talked about zero phase filters, and also commented that they are non-causal, necessarily non-causal, and therefore cannot be realized in real time. What can be realized in real time are the linear phase filters, and linear phase is an extremely important criterion in any system, transmission or otherwise, and we said that only FIR filters can realize exact linear phase. And we also stated that the condition for linear phase is that the impulse response should be either symmetric or antisymmetric, h of n minus n, the filter being of length equal to n plus 1. Capital N is the order of the filter. Now, depending on even or odd length, and depending on symmetry or antisymmetry, we stated that we have 4 types of filters, of which we discussed types 1 and 2. Type 1 was symmetric, h of n equal to h of n minus n, and n plus 1 is equal to is odd. So, capital N, the order of the filter is even, and under this condition we showed that h of z for type 1 is z to the minus n h of z inverse, z to the minus n h of z inverse, which shows, as in all pass filters, that if z0 is a 0, then 1 by Z0 is also a 0. So, the zeros of it applies to all. It applies to all the types, type 1, type 2, type 3, type 4. This is true for type 1 and also type 2, this relationship. So, zeros occur in reciprocal pairs, and we also showed that since capital N is even in type 1, h of 1 is equal to h of 1 and h of minus 1 is equal to h of minus 1, and therefore, there are no restrictions. In other words, type 1 filter does not have a 0 on the unit circle, okay, unless you introduce it intentionally, but the type 1 filter does not have a 0. And in type 2, the length n is odd, not the length, the order n, capital N is odd, and therefore, if I substitute in this relation z equal to 1, then h of 1 is h of 1, but h of minus 1, because capital N is odd, is minus h of minus 1, which means that h of minus 1 is equal to 0. This means that h of z must have a 0 at minus 1. In other words, I must have a factor 1 plus z inverse, and the consequence of this, well, if I show the location of the 0, I must have a 0 at z equal to minus 1, and the consequence of this is that high pass filter is not possible, because high pass filter requires unity magnitude at z equal to minus 1 or omega equal to pi. If it is identically equal to 0, obviously we cannot have a high pass filter. If we cannot have a high pass filter, can we have a band stop filter? A band stop filter also requires unity magnitude at omega equal to 0 as well as omega equal to pi, and therefore band stop is also not possible. HPF and BSF of the type that we have been discussing are not possible. Agreed? Let us go to type 3. We shall have more fun in type 3 filters. Type 3 is, first is antisymmetry, that is h of n is equal to minus h of n minus n. Length in type 3 n plus 1 is equal to odd. Therefore, capital N, the order of the filter is even. Okay, order is even. Now, let us take capital N equal to, let us say 8, as we did earlier. To concretize our idea, we take an example. So, capital N equal to 8, therefore, we have 0, 1, 2, 3, 4, 5, 6, 7 and 8. And the pairings are H0 with H8, but they are not equal now, they are equal and opposite because of antisymmetry. So, H8 is equal to minus H0, all right. Similarly, H1 is minus H7, H2 is minus H6, H3 is minus H5 and H4 is minus H4, and therefore, H4 is identically equal to 0. This is the axis of symmetry. Therefore, in general, h of n by 2 shall be equal to 0, and this introduces further restrictions, as we shall see, but let us first see the shape of the form of the frequency response. For this particular example, capital H of z shall be equal to h naught plus h1 z inverse plus h2 z to the minus 2 plus h3 z to the minus 3, and then we do not have an h4. H4, the middle sample, is identically equal to 0, then H5 is the same as minus H3, therefore I shall have minus z to the minus 3. Is that okay? No, z to the minus 5, H5. H6 is the same as minus H2 and therefore z to the minus 6. Agreed? H7 is minus H1, therefore I shall have minus z to the 7, and H8 is minus H0, therefore I shall have 1 minus z to the minus 8. This is the transfer function, from which now, well, before we go to the next step, suppose we change z inverse to z, all right, then how can we regain hz from this? We multiply by z to the minus 8, z to the minus 8, but the signs are interchanged. You see, if I make 1 minus z to the 8, then I multiply by z to the minus 8, so I get z to the minus 8 minus 1, and therefore I shall require a negative sign. So h of z, in general, h n of z shall be equal to minus, this is the difference. In anti-symmetry, a negative sign comes here, otherwise they are the same. For types 1 and 2, symmetrical impulse response, the sign here is positive. For types 3 and 4, both of them, the sign here is negative. And this is where further restrictions on type 3 comes. Okay. In this particular case, capital H of e to the j omega shall be, if I take z to the minus 4 outside, then I shall have e to the minus j omega by 4. If it is difficult to see, tell me, then I shall write the total expression. I am trying to avoid one step of algebra. I put here z equal to e to the j omega, and then I can take z to the minus 4 out, which is e to the minus j omega by 4. Then what shall I have here? Twice?
So 4 omega it should be. Omega by 4.
That is correct. I will rewrite it. H of e to the j omega shall be equal to e to the minus j 4 omega, then inside bracket I shall have z to the 4 minus z to the minus 4. So it will be twice j h naught sine of 4 omega. The next term would be twice j h1 sine of 3 omega. Similarly, twice j h2 sine of 2 omega plus twice j h3 sine of omega, right? This is what I shall get. I write this j did not come in types 1 and 2 because it was symmetry, and e to the j theta plus e to the minus j theta was a real quantity, twice cosine theta. Here e to the j theta minus e to the minus j theta is twice j sine theta. You see, the difference is that in symmetry cosine functions come, in anti-symmetry sine functions come. In addition, a factor j comes, which can be taken care of by a phase shift of pi by 2, and therefore I can write this as e to the minus j 4 omega e to the j pi by 2 then I can write this twice, 2 also can be taken out, summation h of, now let us see, 4 minus n sine of n omega. Is that right? Where n goes from 1 to 4. Okay. Right? And in general, if I if I write for nth order, h sub n of e to the j omega shall be equal to twice e to the minus j n by 2 omega e to the j pi by 2, then summation n equal to 1, upper limit is n by 2, h of n by 2 minus n sine of n omega. This is the general expression. Have I done this correctly? I think so. You see, the phase shift now is minus n by 2 omega phi plus pi by 2 plus possibility of this real function, which is a pseudo magnitude. This can also have a change of sign, and therefore you must admit a beta. But tau sub g of omega, which is the negative gradient of phase, is equal to minus n by 2. This is plus n by 2, agreed. Negative gradient of phase, so plus n by 2. The other thing that one must notice is that h n of z is equal to minus z to the minus n h n of z inverse. So as far as zeros are concerned, zeros occur in reciprocal pairs, no problem. But you notice now, for type 3 capital N is even. Type 3 capital N is, the order is even, the length is odd. Okay, and you notice that h n of 1 is equal to minus h n of 1, which means that h of 1 is 0. Agreed? Similarly, h, let us drop the subscript n, h of minus 1, because capital N is even, minus 1 to the power even is also plus 1, and therefore this is also minus h of minus 1, which means that h of minus 1 is equal to 0. In terms of zeros, obviously we have zeros at plus 1 as well as minus 1, and therefore for type 3 the transfer function the transfer function h of z shall have a factor 1 plus z inverse and also 1 minus z inverse, some other transfer function h1 of z. Is h1 of z linear phase? Is this linear phase? Yes or no? It has to be. There is no alternative. This is linear phase. This is linear phase. So from linear phase you are subtracting 2 linear phase. The rest must also be linear phase. Otherwise the sum cannot be linear phase. So this is also linear phase. It contains the other zeros which occur in reciprocal pairs. What about this 0? Why didn't it occur in reciprocal pair? Because the reciprocal of plus 1 is plus 1 itself. So it can occur singly. The reciprocal of minus 1 is also minus 1, and therefore that can also occur singly. But the others, h1 of z, the rest of the function, may not contain another 0 at plus 1 or minus 1. I said may not. Why not? It may also contain. For example, this 0 can occur with multiplicity 2 or 3, whatever it is. Agreed? Okay. So it must at least there is one 0 at plus 1 as well as minus 1, and therefore HPF, LPF and BSF not possible. Not possible. The only thing that you can do is type 3 is band pass filter. Okay. Now let us talk of type 4. In type 4, h of n is equal to minus h of n minus n, length n plus 1 is equal to even. So capital N order is odd. And if we take, let us say, capital N equal to 7 as an example, then my pairing would be like this: 0, 1, 2, 3, 4, 5, 6, 7. 0 with 7, H0 shall be equal to minus H7, H1 should be minus H6, H2 would be minus H5 and H3 at minus H4. There is no loner here. The symmetry is around 3.5 where there exists no sample. All right. So, if I write the frequency response, shall we omit one step? We can write the frequency response directly. H of e to the j omega would be equal to e to the minus j omega 7 by 2, and then we shall have a j also, and because of subtraction there shall be a factor 2j, and all the functions inside shall be sine, and the first one would be 2h naught sine of no 2 okay, sine of 7 omega by 2, is that right? They are not integral multiple of omega, plus h1 sine of 5 omega by 2 plus h2 sine of 3 omega by 2 plus h3 sine of omega by 2, and in general hn of e to the j omega shall be equal to twice e to the minus j omega, yes, n by 2. Now it is not an integer, there is a half sample extra delay, then e to the power j pi by 2 summation n equal to 1 to
capital N minus 1, n by 2 minus 1.
n plus 1 by 2. Okay. Then h of, yes, minus n sine of omega n minus half. That is correct. This is the correct expression. And here also the phase is minus omega n by 2 plus pi by 2 plus beta. So, the tau sub g of omega is equal to n by 2, half sample, extra half sample delay, which creates problems in actual hardware realization, but that can also be surmounted. The problem can be surmounted. Now, h of z here is minus z to the minus n, h of z inverse, and capital N is even. No, I am sorry, capital N is odd. Okay, odd. So, h of 1 shall be equal to minus h of 1. but no, capital N is odd. Therefore, 1 plus 1 to the power odd is also plus 1, but h of minus 1 is equal to h of minus 1, because the negative sign and the negative sign here, they make a positive sign, and therefore there is no 0 at minus 1. In other words, h of 1 is already equal to 0, and therefore you have a 0 here. All right, you have a 0 here. In other words, h of z shall have a factor 1 minus z to the minus 1 h 1 of z, and therefore low pass filter is not possible. Agreed? Because z equal to 1 corresponds to omega equal to 0. LPF, if LPF is not possible, band stop filter is also not possible. So you see, types 2, 3 and 4, they are restricted. Type 3 is the most restricted one. You can only design band pass filters. Okay? Type 1 is the most versatile, you can design any kind of filter. So type 1 is the most favored one. If you can do it type 1, no problem. Type 1 also does not give a non-integer delay, it gives an integral number of samples delay. So type 1 is the most favored one. Nevertheless, in situations where you require a 0 at z equal to 1 or z equal to minus 1, you use the other types. For example, if you want to design a differentiator, okay, a differentiator, what is the magnitude response of a differentiator? It's a straight line. For a differentiator, h of e to the j omega, differentiator, an ideal differentiator would be of the form j omega minus pi less than omega less than pi, and therefore its magnitude is 0 at omega equal to 0, right? What type would be suitable? At omega equal to 0, that is z equal to 1, it is 0, so type 4. Type 4 has a 0 at z equal to 1. Type 4 filter would be the most suitable one for this. Okay? So there are situations where one requires one of these types, but if it's a general filter design problem, you have to design low pass, high pass, band stop and so on, and then type 1 is the most favored one. In general, you have also seen that for a linear phase FIR, the expression is of the form minus j omega n by 2, capital N is even or odd, all of them have n by 2 number of delays, and then you have an additional factor of e to the j, let us say gamma, where gamma can be 0 or pi by 2. Agreed? Gamma is 0 for types 1 and 2, gamma is pi by 2 for types 3 and 4, and then you have a pseudo magnitude function. The most general form of a linear phase FIR is this, the frequency response. So the phase is minus omega n by 2 plus gamma plus beta, which can be 0 or an integral multiple of pi. Agreed? The group delay is still n by 2. Now let us look at the zeros. Well, the transfer function is in general of the form plus minus z to the minus n h of z inverse. So what we said about zeros of types 1 and 2 are valid here also. I mean, even if there is a negative sign, it does not change the nature of the zeros. The zeros still occur in reciprocal pairs. Now we are going to play a game. I am going to give you the location of a 0 and I want you to tell me where its reciprocal would be. If we have a 0 here at plus 1, then we don't require any more. It can occur singly or multiply or whatever it is, because reciprocal of plus 1 is plus 1. Similarly, a 0 here does not require a reciprocal. But if I have a 0 here plus j, what is its reciprocal? Minus j. And but do I have to force the function to have a 0 at minus j, or does it automatically come? It automatically comes with real impulse response. It shall automatically come. If I have a 0 at plus j, I must have a 0 at minus j. But this is not true. If I have a 0, let me change the color. If I have a 0 here, then of course there must be a 0 here, that is j r is less than 1, then it must be 0. But what is the problem now? There must be a 0 at j by r and minus j by r. This is the reciprocal of this, not of this, and this is the reciprocal of this. Okay? So these are possible. Now if I have a 0 here, some other color, if I have a 0 here, let us say at plus r, then I must have a 0 at 1 by r. If it is a minus r, then I must have at minus r. But if I have a 0 here, let us say here, then I must have a 0 here for real coefficient, and I must have zeros here and here, this being the reciprocal of this and this being the reciprocal of this. So 4 of them, if there is a complex 0, then the zeros, complex 0, not purely imaginary. Purely imaginary, we have seen, they must also occur in groups of 4. Why groups of 4? Because real coefficient demands that if I have a 0 at jr, I must have a 0 at minus jr. Okay? So complex or purely imaginary zeros, except if the 0 occurs on the unit circle. If it occurs in the unit circle, then they occur in pairs, and they do not reflect any special property of linear phase. Okay? But if it exists outside the unit circle on the imaginary axis, then they must occur in sets of 4, and this is technically called zeros. Complex zeros occur in quads. Okay? Quads is a short term for quadruplet. Okay? So for linear phase filters, suppose I I tell you that all right, let's take an example. Suppose I say I have a 5th order filter, 5th order linear phase FIR filter, having one of the zeros at half e to the power j pi by 4. Can you construct the filter? Total filter. I have given you only this piece of information. Yes? How many choices do you have? 4 of the zeros shall be determined by this. You shall have 1 minus z inverse half e to the j pi by 4 as one of the factors. Then you shall have 1 minus z inverse half e to the minus j pi by 4. Then 1 minus z inverse 2 e to the j pi by 4. 1 minus z inverse 2 e to the minus j pi by 4. So these 4 factors I can write. What would be your choice for the 5th factor? 5th factor, I have said the order is 5. You have been able to construct 4 factors. What will be the 5th one? Something which occurs singly. What occurs singly? Either at plus 1 or minus 1, and therefore you have 2 choices, 1 plus minus Z inverse. You have no other choice. And if you choose 1 plus, then you have chosen which type? 0 at minus 1. Is it type 1? No, type 1 cannot have a 0 at minus 1. Type 2. No, it cannot be type 3. Type 3 requires a 0 at minus 1 and also plus 1. You must be careful. Type 2. On the other hand, if you choose 1 minus, then you have a type 4. Okay. So, this is the kind of problem that one obtains from partial information about what you want. You can construct the whole given only this much of information because of the property of linear phase functions. To summarize, type 1 is versatile, no 0 at plus 1 or minus 1, all kinds of filters can be designed. Type 2 is not versatile, HPF is not possible in type 2. If HPF is not possible, band stop is also not possible. Type 3 is severely restricted, no low pass, no high pass, no band stop. It is only suitable for band pass filter. Type 4, no low pass, no band stop. Okay? And you know these depend on the 0 locations. Where it is restricted, there is a 0 at plus 1 or minus 1 or both. Agreed? So that summarizes our discussion of linear phase. Now we go to complementary filters. Complementary filters. And the complementary filters can be of various types. It can be delay complementary, it can be magnitude complementary, power complementary, or we shall have one more, all pass complementary. Okay. First we consider delay complementary. Okay. A set of filters, the definition, a set of filters Hiz I equal to 0 to L minus 1, a set of capital N L number of filters Hiz are said to be delay complementary if and only if the summation of them Hiz I equal to 0 to L minus 1 is equal to some constant beta multiplied by a pure delay z to the minus n0. N0 is a positive integer. If the sum of the filters make a pure delay, the magnitude may not be unity, it does not matter. Magnitude may be a constant beta, but the sum of the filters should make a pure delay. For example, if we have L equal to 2, then H0 z plus H1 z should be equal to beta z to the power minus n0. If H0 and H1 form a delay complementary pair, the sum of the two, I can tell you very simple examples. H0 can be 1, H0 can be 1, and H1, can you give me a simple function for H1 which will make them delay complementary? Minus 1 plus Z inverse. Agreed? These are delay complementary. These are trivial examples. There many other examples which we shall take account of. But now we shall require your complete attention. Suppose H naught is type 1 linear phase of length capital M, which is equal to odd. Type 1 has to be odd length, 2k plus 1, all right. And suppose the magnitude of H naught e to the j omega, I need your complete attention now. Suppose it is a low pass filter, and low pass filter, as you know, has to have a tolerance in the pass band and a tolerance in the stop band. Suppose the tolerance scheme is this, that is, the characteristic must lie between 0 and omega p between two levels, let us say 1 plus delta p and 1 minus delta p. Within this range, it can be monotonic, it can be with ripple. Then we have an omega s, and the stop band extends from omega s to pi, and let us say the tolerance here is delta s. Mind you, we are plotting the magnitude, not the pseudo magnitude. If the function H naught e to the j omega, if the pseudo function corresponding to H naught has a 0, where can this 0 occur? At a 0, you know, there will be a phase change of pi. At a 0, the sign of the pseudo magnitude changes from positive to negative or negative to positive. Okay? If the pseudo function corresponding to H naught has a 0, where can it occur? Can it occur within 0 to omega p? No, it cannot. Can it occur between omega p and omega s? Yes or no? No. If it occurs somewhere here, if the magnitude comes to 0 here, then the stop band should not have started at omega s, it should have started earlier. Isn't that right? Let us draw it. Suppose it comes like this, then the stop band would have started here. So, the 0, if at all there is a phase change, if at all there is a sign change, it should occur between omega s and pi. Agreed? Is the point clear? Pseudo magnitude cannot have a change of sign between 0 and omega s, because between 0 and omega p it is the pass band. In pass band it cannot have a 0. Pass band, the magnitude cannot go to 0. In the transition band omega p to omega s, it cannot go to 0, because then the stop band would have started earlier. Since the stop band has started at omega s, if at all there is a change of sign, the change of sign shall occur between omega s and pi. This point clear? Now, suppose we want to construct from this H naught, we want to construct a delay complementary filter H1 of z, and suppose well, first, what is the form of H naught of e to the j omega? It is of the form e to the minus j. Yes, now your test whether you have understood type 1 filters or not. What would be the factor here? The length was 2k plus 1. So, what would be the factor here? K, not 2k. N by 2, order divided by 2, multiplied by, let us say, H naught omega, the pseudo magnitude function. Okay? We want a delay complementary function h1 of e to the j omega, okay, what will be the delay of what can be the delay of this? If they are delay complementary h1 and h0, what can be the delay of this? It has to be, if h1 is also a linear phase filter, then it has to be k minus k omega. In other words, it has to be equal to minus j k omega. It cannot be otherwise. If they are delay complementary, if their sum is e to the minus j, e to the z to the minus n0, then the delay must be equal to k. It cannot be otherwise. And therefore, h1 of e to the j omega would be of the form e to the minus j k omega. What is beta here? Beta is 1. We have normalized it to 1, and n0 is equal to k. All right. So, h1 of e to the j omega must be 1 minus this, okay. The sum of the two is e to the minus j k omega, and h naught is this, and therefore h1 must be of this form. The question now is, what will h1 be? What kind of a filter will h1 be? High pass. It has to be high pass. Okay, that's our first. Now, what would be the n0 equal to k? Z to the minus n0, so n0 has been taken to be equal to k. Okay, if both are linear phase, then it cannot be otherwise. The sum of a linear phase of order twice k and another linear phase of order twice k will give you a delay of k. All right. Now, what will be the form of h1? Okay, let's write h1 as e to the minus j k omega. Let's write 1 minus h naught as h1 hat of omega, h1 tilde of omega. What will be the form of h1 tilde of omega? Remember, we are now plotting not the magnitude but the pseudo magnitude. Now, in the pass band of h naught, the tolerance was 1 plus delta p and 1 minus delta p. So, what would be the corresponding pseudo magnitude? Plus delta p and minus delta p, because this is 1 minus h naught. So, 1 minus 1 plus delta p and 1 minus delta p, and therefore, our tolerance scheme for h1 shall be plus delta p and minus delta p. In other words, the tolerance in this, well, what is this frequency? Omega p. Now, at omega s, the tolerance in h naught of omega was delta s, and we said that it can, within omega s to pi, there can be a change of sign, and therefore, what would be the tolerance for the high pass filter? Yes, 1 plus delta s and 1 minus delta s. If there is a change of sign and the magnitude is restricted by delta s, it can be 1 plus delta s. Remember, h1 tilde of omega is 1 minus h naught tilde of omega, and therefore, when h naught of omega is plus delta s, we have 1 minus delta s. H naught of omega could also go to minus delta s. Therefore, our tolerance is 1 plus delta S, 1 minus minus delta S. Is the point clear? And therefore, the tolerance by delay complementary transformation, the tolerance scheme that we get is not the same as that of the filter from which we derive it. The tolerance here in the stop band is twice delta P, and the tolerance here is twice delta S. On the other hand, in the low pass filter, the tolerance was twice delta P and delta S only. Is the point clear? Okay. Now, we have a few minutes. So, in general, it stands to reason that the delay complementary filter of a low pass filter shall be a high pass filter and vice versa. But the tolerance schemes are different, has to be worked out. Okay. For a band pass filter, the delay complementary filter will be a band stop filter. They will be complementary to each other and vice versa. For an all pass filter, the delay complementary filter shall also be all pass. So, let us now talk about all pass complementary filter. Shall we take only two? It can be generalized. A set Hi, I equal to 0 to L minus 1 is all pass complementary if their sum I equal to 1 to L minus 1 is an all pass filter. That is as simple as that. Delay complementary filter is also all pass complementary. Isn't that right? Is that a difficult statement? Delay complementary filter H naught plus H1 was equal to beta times z to the power minus n0. What is this filter? Beta times z to the minus n0? All pass. Okay. Now, this is not restricted to FIR only. A delay all pass complementary filter AZ may not be FIR. Similarly, HIZ may not be FIR. It is a most general type of filter. If the components of the set are FIR, then delay complementary is a special case of all pass complementary. Okay. Two IIR filters may not add to give you z to the power minus n0. So, this is more general, and one of the very simple examples of delay complementary filter is, suppose L equal to 2 and suppose I take an H0z which is equal to half of A0z plus A1z. Suppose I have an H0z which is the sum of two all pass filters A0z and A1z. Okay. Then its all pass complementary filter H1z shall be equal to half of A0z minus A1z. This is one example. It could be the other way around also. Now, let me also point out that this sum can be either positive or negative. As far as magnitude is concerned, it does not matter. If it is negative, you have added a phase of pi. Okay. So, you see, when I add these two, what do I get? H naught plus H1 is equal to A naught Z. Agree? So, this is an example of all pass complementary filters. Similarly, one can define, now you can see now how all pass is gradually coming into the picture. In fact, I have already stated that if you can design an all pass filter, you can design any other kind of filter. Okay. We will conclude this class with the definition of power complementary filters. Power complementary means that a set Hi is power complementary if their powers, which are characterized by magnitude squared of the transfer function, if their powers add up to a normalized value of 1. This is true for all omega. At all frequencies, if the powers add up to 1, we did not say energy, this is not energy. Why is it power? Because for energy you require 1 by 2 pi integral of this with respect to omega. This is the power, sum of the powers should be normalized to 1. And this means if it is true for all omega, then by analytic continuation you can also say that Hi of z inverse, after all this power is nothing but this with z equal to e to the power j omega, I equal to 0 to L minus 1 should be equal to 1. All right. And suppose capital L is equal to 2, that is 2 power complementary filters. Next time we will start with a very interesting observation, that 2 filters which are all pass complementary, that is the sum of them is all pass, are also power complementary. That is, if you make H naught z inverse, H naught z inverse plus H1 z inverse, you can show that this is equal to 1. And this is why we took that factor half. If we take that factor half, if H naught is half A naught plus A1, H1 is half A naught minus A1, then it can be shown that this is also true. Therefore, this set of filters is all pass complementary as well as power complementary, and they are known as doubly complementary filters. Doubly complementary filters. They are very important applications, and we shall look at some of the applications at a later date. That is all for today.